Hi, and welcome to our CS225 Final project presentation. My name is Jay.
My name is Suwen.
I'm Jiewen.
I'm Yijia.
This presentation is going to be divided into three different parts: goals, development, and conclusions. So without any further ado, let's jump right in. For our initial goal of the project, we wanted to use graph algorithms to find out the shortest path between two airports with the minimum number of transfers and compare the runtime and effectiveness of our algorithms using various airport data. As for the data sets, we decided to use the data from openflights.org, and our project mainly focuses on two subsets of the data, the airport subset and the routes subset. A sample of the airport subset is shown on the right. We can see that it contains the airport ID, the airport name, the city of the airport, and latitude and longitude, which we will later use to calculate the distance and formulate the graph. The data is stored in both CSV and DAT format after getting rid of all the unwanted or error data of the original subsets, since we realize that the real-world data can sometimes be big and messy to handle. For our graph structure, we will use the airport ID as nodes and the path between them as edges. And since the OpenFlights datasets does not offer data regarding the distance of the flight routes, in order to find the distance between two airports with only the longitude and latitude data available, we use the Habersign formula. The Habersign formula can tell us the great circle distance between 2 points on a sphere. So here the sphere will be the planet Earth, given their longitude and latitudes. So here we can see the Habersign formula, and phi 1 and phi 2 here represents the latitude of point 1 and point 2, and lambda 1 and 2 represents the longitude of point 1 and point 2 respectively. As for our project development, Yijia is going to first talk about the BFS Traversal. Yijia.
Our project consists of three main algorithms. The first component is the BFS Traversal, which we wrote in order to find the route from start airport to destination airport, then stop search. After that, we coded Dijkstra's algorithm in order to find the shortest path between one airport and any other airport in our dataset. After that, we implemented a landmark path using Dijkstra's algorithm in order to find shortest distance between start and destination airports going through landmark. And then we implemented test cases to make sure our program is valid and efficient. Our BFS Traversal is the first algorithm in our project. In order to implement BFS, we actually use the queue. We first mark all our airports as not visited and initialize BFS by enqueuing or adding our source and starting node. After that, we enter the loop in which, while the queue was not empty, we process this node in the case statement, deleting and printing out the node. Then we add that node's adjacent neighbors to the back of the queue and then continued along the loop. If the current node equals the destination node, that means our destination is reached and we should stop. However, if our current node is not equal to the destination node, that means no path could be found between start and destination using BFS. In the end, we return the airport closed path. The BFS traversal for finding the route from start airport and destination airport is not finished. Next, Suwen will talk about Dijkstra's algorithm.
Okay, so now it's my turn to talk about the Dijkstra algorithm. First, the reason for us to use this algorithm is that it can be used on weighted edges to find the shortest path between two nodes, which is exactly what we need to do for this project. Then in order to implement this algorithm, we need three things: a visited set, a tentative distance value for each node, and a priority queue. Okay, next slide. So specifically in our project, the parameters for this function is start and destination to int representing the two nodes that we are trying to find the shortest path in between. At the very beginning, we will check the edge cases. Then we use three vectors: distance from start, previous, and visited to keep track of our visited set, tentative distance value for each node, and the priority queue. Before anything else, we will set all distance to infinity, since we don't know any distance yet. At this stage, our visited vector is empty. Then we will start to deal with each specific node, such as adding them to the priority queue and pop elements from the priority queue until we reach the end. Afterwards, we will trace back from destination to start and convert airports IDs to airport code. And that's basically what we do for the Dijkstra algorithm.
Okay. Okay, and then this is about landmark algorithm. In general, there are three procedures for this algorithm. Step 1, we determine one vertex as landmark between two nodes. Step 2, we can calculate the shortest path between each node and the landmark. For the last step, we add two parts together and choose the minimum one. So in our project, our goal is to find the shortest distance between two airports. We randomly choose one airport between the starting point and the ending point. Firstly, we use the Dijkstra's algorithm to calculate the distance from the starting airport to the landmark, and then the distance from the landmark to the ending airport. Secondly, for the situation that there is no path between two airports, we will return t. Otherwise, we would add two distance together as the path we get from the landmark algorithm. Okay, next slide. Compare with the Dijkstra's algorithm, landmark algorithm cannot guarantee to have the shortest path. Sometimes a landmark would add more distance. You can see in the picture above, the total distance with landmark, which is more than 20,000 kilometers. That is more than the distance we found without landmark. And it would also include more flights when we have a landmark. Okay, and then Suwen will give you some conclusion.
Okay, so this is the example we run on our project. First, we try to find the shortest path between CMI and SMF, and we input the landmark stop as DFW. After the code runs successfully, it shows us that the path with the least number of connecting flights, the path with the shortest distance traveled, the total distance of flights, the shortest distance from CMI to SMF with a pit stop at DFW, and its total distance. In addition, we also try cases such as setting the start as JFK and destination as HF and HFN, and our code successfully tells us that there are no connecting flights between those two places. Overall, we input different sets of start, destination, and landmarks into our program, and all of them generate valid results. By the way, this also serves as our test cases. All in all, our project is able to process the data from the open flights data set and find the shortest, most efficient path between two given input airports. That's all, thank you.